You are in a window seat, somewhere over the ocean. The cabin is calm. A drink sits on the tray in front of you, perfectly still. Then the aircraft drops. Not far, just enough to lift you against the seatbelt, enough to make the ice jump in the glass and turn every head toward the window. A few seconds later, it is over. The wing was never in danger. The sky outside is empty. No storm, no cloud, nothing to see. What just moved a 300-ton machine was turbulence. The everyday roughness of moving air and water. The same thing you see when cream curls into coffee or when smoke breaks apart above a candle. It is one of the most common phenomena on Earth, and it is, quietly, one of the things physics still cannot solve. To understand why that is strange, you have to know what we do have. In the 1800s, two physicists, Claude-Louis Navier and George Stokes, wrote down a set of equations that describe how a fluid moves. Any fluid. Air, water, blood, the atmosphere of a star. Give the equations a starting point, and in principle, they tell you everything the fluid will do next. These equations are not controversial. Engineers use them every day. As far as we can tell, they are correct. And that is exactly what makes turbulence so unsettling. We are not missing the law. We have had the law for more than a century. What we cannot do is solve it. Here is the precise problem. For smooth, gentle flow, the equations behave, but turn up the speed, and the flow breaks into a storm of swirls inside swirls, and the mathematics becomes something no one can fully tame. To this day, no one has proven that the equations always have a sensible solution in 3 dimensions. No one has ruled out that, under the right conditions, they could break down into nonsense. That single question is considered so hard and so important that in the year 2000, it was named one of the 7 Millennium Prize problems in mathematics. There is a prize of $1 million for an answer. More than 20 years later, it is unclaimed. And solving those equations, the prize committee noted, would only be the first step toward understanding turbulence itself. So how far have we actually gotten? The story really begins in 1883, in a laboratory in Manchester. A physicist named Osborne Reynolds ran water through a glass pipe and injected a thin thread of dye. At low speed, the dye ran in a single straight line, smooth, orderly flow. Then he opened the valve. At some point, the thread shivered, curled, and burst apart into chaos. Reynolds found a way to predict, roughly, when this would happen. A single number, now called the Reynolds number, that still sits at the heart of fluid physics. But he could not explain the moment of transition itself, and more than a century later, neither can we. In the smooth state, the flow is perfectly stable on paper. The math says small disturbances should simply fade away. Yet in the real world, the flow tips into turbulence anyway. Modern experiments describe that transition, in plain scientific language, as abrupt and mysterious. There was, though, one genuine breakthrough. In 1922, an English scientist named Lewis Fry Richardson pictured turbulence as a cascade. Big whirls, he said, break into smaller whirls, which break into smaller ones still, all the way down until the tiniest eddies are smoothed away by the fluid's own stickiness. 2 decades later, the Russian mathematician Andrei Kolmogorov turned that picture into numbers. He predicted exactly how the energy of a turbulent flow should be shared across those different scales. A precise mathematical curve, now known as the 5/3 law. And when scientists measure real turbulence, in wind tunnels, in the ocean, in the open atmosphere, the curve is there. It holds across flows that could hardly be more different. It was, and still is, turbulence's most beautiful result. But notice what that result actually is. It describes turbulence on average. It tells you how the chaos behaves in the long run, across many swirls. It does not tell you what any single eddy will do at any single moment. And when you look closely, even the average is not perfect. Real turbulence comes in bursts, sudden, violent concentrations of motion that the clean theory does not fully capture. Physicists call this intermittency, and describing it from first principles is an unsolved problem inside the larger one. You might think the answer is obvious. Let a computer do it. Simply simulate every swirl. But here the numbers turn cruel. Each time you want to resolve a faster, finer flow, the amount of computation needed explodes. For something the size of an airliner's wing, tracking every eddy is simply beyond any machine we have, or expect to have. That is why, deep in the 21st century, aircraft are still tested in wind tunnels. We cannot calculate the air. We still have to go and watch it. And there's a newer reason this matters. The turbulence that shakes aircraft is not staying the same. When researchers at the University of Reading studied 4 decades of atmospheric data, they found something striking. Over the North Atlantic, one of the busiest flight corridors on Earth, the yearly amount of severe, clear air turbulence rose by about 55% between 1979 and 2020. The suspected cause is climate change. A warming planet is sharpening the temperature differences that drive the jet stream, and a sharper jet stream tears harder at the air around it. And the most dangerous kind gives no warning at all. It forms in a clear sky, invisible to a plane's weather radar. In 2024, a Singapore Airlines flight hit turbulence so violent that 1 passenger died and dozens were injured. That particular jolt came from a towering storm cloud, not from clear air. But it was a reminder of what a few seconds of untamed fluid can do. So where does this leave the science? Not with rival theories of what turbulence is. Everyone agrees on the equations. The disagreement is about how to finally crack them. One camp works with pen and paper, trying to prove rigorously what the equations can and cannot do. In 2025, mathematicians reported a rare step forward, a way to capture those violent bursts of energy inside a rigorous framework. It was real progress. It was also nowhere near a full solution. Another camp builds ever cleverer approximations, models that do not track every swirl, but capture enough to design a wing or forecast a storm. They work well enough to fly on, and they are, by their own admission, approximations, not understanding. Both approaches circle the same locked door from different sides. Neither has opened it. It is worth being clear about how much we do know, because turbulence is not a mystery in the way a ghost story is. We have the exact equations. We can predict with a single number roughly when smooth flow will turn rough. We can describe with real precision how energy spreads through the chaos on average. We can model turbulence well enough to cross oceans in a metal tube at 8/10 the speed of sound. This is one of the most useful bodies of knowledge in all of engineering. The gap is specific. We can describe turbulence. We cannot, from the fundamental laws alone, fully solve it or predict it. So what would it take to close that gap? At the very least, an answer to the Millennium Problem, a proof of whether the equations of fluid motion always behave, or whether they can break. Beyond that, a way to derive those bursts of intermittency from the laws themselves, instead of fitting them after the fact. And a real theory of that first flicker, the exact instant orderly flow chooses to become chaos. No one knows how far away those answers are. They may come from a piece of mathematics no one has invented yet. They may take another 100 years. Turbulence has already outlasted the lifetimes of everyone who first tried to tame it. There is something humbling in this. We have mapped the inside of the atom and the shape of the early universe. We can predict eclipses centuries in advance, and yet the swirl of cream in a cup, the shudder of air over a wing, the everyday roughness of a flowing stream. That we still cannot follow all the way down. The universe keeps some of its quietest secrets not in the far reaches of space, but in a glass of water on a tray table somewhere over the ocean, sitting perfectly still, until, for a few seconds, it isn't.